All right. So the other day we looked at a circuit. It was an RC circuit. And what we did the other day was I said I had a constant input. And if I did my KVL, I would end up with this differential equation. In this particular case, my source, x of t, is a sinusoidal source. And again, I use that term sinusoidal, whether it's cosine or sine, all right, because I can relate the two of them together. All right, so it's a sinusoidal source. So I talked about this u of t thing the other day. What did I call u of t? Step function, right? And I basically said that for all intents and purposes, it just means that I can rewrite this as 0.1 dy by dt plus 3 y of t equal to 4 cosine 300t plus 20 degrees for t for what condition on t? Yeah. Yeah, greater than or equal to 0, let's say. Okay. All right. So we've got an initial condition. So in this case, for this circuit, Y apparently is the voltage across the capacitor, X is the input. All right. Now, what do we do to approach this thing? We solve the homogeneous, which gives us the transient response. Solve the non-homogeneous, which gives us the steady state or particular solution. And then step 3 is to basically combine those two things. Okay. So what we did the other day is we basically said for the transient, we guess y equals ae to the st. Okay. And for the steady state condition, we said we basically used anytime we've got these special inputs, which are all related to the exponential. So whether I have a constant input, an exponential, or a sine wave, I basically have a special situation where I guess something that looks exactly like what I put in. Again, so I call this x of t. I call it the input, right? It's what I'm putting into the circuit or the system, right? So my output is going to look something like the input. And when I say something like the input, if I put in an exponential, I'm going to get an exponential out. If I put a constant in, I'm going to get a constant out. If I put a sine wave in, I'm going to get a sine wave out. All right. And so we have that basic approach. And so what we do is we guess a form to the solution, and then we solve to figure out some unknown coefficients. Okay. So looking real quick, let's go through this guy, right, using those 3 steps. So instead of the u of t, I'm going to just cross that out and say it's equal to that for t greater than or equal to 0. All right, so what's my homogeneous equation that goes with this equation in step 1? What's my homogeneous equation?
0.1 dy dt plus 3y dt.
Yep, I say 0.1, and I usually say dy sub c by dt, because what I end up saying is that the total solution, y of t, is equal to y sub c, the transient, plus y sub p, the particular or steady state. Okay, so I have that. Now, what do I guess here for y sub c? What do I guess for that guy? So what do we say we always guess for the transient? We just talked about it like 5 minutes ago. What do I always guess for this guy? Yep. A e to the st. Technically, with that caveat that a is not equal to 0. All right. So I guess that and I plug it in, right? So I say 0.01 d by dt of a e to the st plus 3 times a e to the st equals 0. Now, again, what happens to that derivative of e to the st? What's the derivative of e to the st? Se to the st. So I end up with 0.1 s. All right. And then rearranging all this stuff, I get a e to the st plus 3 times a e. Oops. AE to the ST equals 0. What's special about this? I got E to the ST and A in each of these. So I said I got AE to the ST times 0.1 S plus 3 equals 0. Which one of those is equal to 0? Yeah, only this term right here. We called that guy, we called it the characteristic equation. All right, I'm going to use that term more as we get into second order. But basically, I get that 0.1 S plus 3 equals 0, or that S equals 3 over 0.1 with a negative sign. So S should be negative. That's usually what we're looking for it to be. Okay. All right. So we've got the transient response. I don't know what A is, but I can't figure that out until the third step. I need to use my initial condition to do that. Okay. All right. So keep rolling. All right. Step 2. This is where I sort of ended up the other day. All right. And so what I could do is I can guess if I have a, again, this is my I call this side always over here. I call this the input. I can guess that the output looks like this. Right? In other words, if I put a sine wave in, I'm always going to get a sine wave out. I can't put a sine wave into a circuit and get an exponential out. Doesn't work like that. If I put a sine wave in, I get a sine wave out. Exponential in, exponential out. Constant in, constant out. The values of those constants and things may be different. But if in other words, if I put what the output and the input always kind of look like each other. Okay. All right. I can guess that. If I guessed that, what would I do? So if I guessed this, what's the next step? Substitute it in, right? So it's going to be ugly. I don't want to go through the math on this for a while, but 0.1, what's the derivative of this guy? Well, it's ugly. It's going to be negative. Instead of calling this 300t, I'm going to basically say that omega is equal to 300, right? And I'm going to say that this is negative omega b. What's the derivative of cosine? Negative sine. So negative omega b sine omega t plus phi. I'm skipping the derivative here. I just went straight to the derivative because I don't want to focus on this too much. 3 times b cosine 300t plus phi equals 4 cosine 300t plus 20 degrees. Okay. It's ugly. For a minute, I'm going to just say, let's just say for sake of argument, that was 0 degrees. Okay. I'm going to get rid of that. All right. Just to be clear, what are the things that I don't know here? And I'm going to call, instead of 300, I'm just going to call this omega and omega. What are the things what the heck am I doing? I just started writing stuff down, right? You guys are just writing it down blindly. What am I doing? Losing my mind. That's one thing. And the phi. All right. So in my guess, right, I'm saying that the output and the input have the same frequency, but I don't know the amplitude of the output, and I don't know the phase shift, phi. So I'm solving for those two things. This guy is ugly. I took the 20 degrees out because it's only going to make it uglier. It's going to take an ugly thing and make it and beat it with an ugly stick. Okay. So crap. Okay, so I want to go into the step 2 for if I went with that for a second, right? And I had guessed that this was my like I did. And I went through this whole thing and plugged it into that particular equation. What I would have to do with that b cosine omega t plus phi is I would end up basically using a bunch of trig identities, breaking this whole thing up, going through these trig identities, and basically I would take the cosine omega t plus phi and I would turn it into basically things that could be related to sine and cosine. I'd end up doing some trigonometry. I'd end up getting an equation that looks like that to solve for b, right? And then I'd do a bunch of trig and I get some answer that looks like this. All right. So you can go back and look at that if you want to. It's ugly. I think you can believe me on that, right? And I even took the 20 degrees out, so that made it prettier, believe it or not. So it's pretty nasty, right? So we don't like to do. I don't like to do this. I don't think many people do. So the question is, do we have an alternative approach? And the alternative approach is basically that when I'm doing this second step, I can rely on this fact right here, right? So for this special class of inputs we have that are related to the exponential, meaning a constant, an exponential, or a sine wave, I can think of all of those things as exponentials, okay? The output that I guess is always going to look like that too. So when I have a sine wave input, I could guess that my output looks similar and I could go through this whole process. Or I could say that it's the real part of that thing. Now, what is the whole process for that part? Real of that thing. What is real? So how does this become a cosine? How do I turn this real of this to a cosine? Why do I know that that's true? Euler's identity, right? The whole Euler's identity thing, right? We've gone through that. E to the j omega t is cosine omega t plus j sine omega t. Go through that whole process, and I can see that the real part of this expression is going to be whatever that is. So where we had left this basically is the other day, as I said, well, I'm still going to guess that the solution has the form that I've shown right here. But I know that that has to be the real part of this thing. Okay. So what I'm going to do to get the steady state solution is I'm going to go through these 5 steps. So I'm going to make this guess. All right, that's step 1. That's the easy step, right? Then what I do is I go to what I call get the equation into the complex exponential form, and then basically go through the rest of these steps here. All right, so I'm going to take you through those steps one by one. So the first thing is I'm going to guess the solution like we did before. So what I'm going to say is that y sub p is equal to this thing, which has to be the real part of this. The fact that that is true is something that you should be comfortable with by the time you take exam 1. Right? This is going to be on exam 1 as a differential equation, but this will be, right? The fact that you need to manipulate that stuff. All right, you need to get comfortable with that. All right, so essentially, I'm going to start on to step 2 here, and I'm going to put everything into this. So I'm going to say 0.1. Well, that is my whole step 1. What I do in step 2 is I say convert this into the complex exponential domain. All right, so what I can do is I can look at this and say, if this is my guess, I can think of for cosine omega t, it's plus 20 degrees. I can think of that also in the complex exponential domain. How does this relate to a complex exponential right here? So in step 2, I basically say, how do I relate this to a complex exponential? This would be the real part of what? Yep. Okay. So what I can do here is convert this into the complex exponential domain. So what I'm going to say is that the equation is now 0.1 dyp by dt plus 3yp equals, I'm just going to drop the whole real part business. Say this is 4e to the j 20 degrees times e to the j 300t. Where I'm going to guess that yp equals what we said on the previous page. like that. I'm going to drop the whole real part business, all right, completely away from this thing. And I'm going to basically go ahead and I'm going to substitute this in there. So this step 2 is basically this, all right? Step 3 is to put the guess into this thing, all right? So let's do that. So I'm going to say I've got 0.1 dyp by dt. And I'm going to say yp we just said was b e to the j angle b e to the j 300t plus 3 times b e to the j angle b e to the j 300t equals 4 e to the j 20 degrees e to the j 300t. Like that. All right. How do I take what do I do here? I take the derivative of the first term. What's the derivative of this first term? How do I take the derivative of that? What's that? Yeah, I can do product rule. It's even simpler than product rule. Get the right idea.
The last part is only a constant, right? We can
Yeah.
just use omega.
This is a constant, right? And I guess to be clear, I was really calling that the magnitude like that, right? Let's be clear like that. Yeah. Magnitude B is a number. E to the J angle B is a number. It's also a constant, right? It's a weird constant, right? So it's a complex constant, but it's a constant nonetheless. Okay. So what's the only part that depends on time there? Yeah, the e to the j omega t. So in this case, e to the j 300t. So if I have constant times e to the at, what's the derivative of constant times e to the at? That's one thing you should know, right? Derivatives and integrals of exponentials, we get them all the time, right? So what do I get with that? Constant times, if I have constant times e to the j little at, or not even the j, just call it that. Because the j blows your mind, and e to the j blows your mind to an even different step. E to the j anything, e to the j angle, like that. That's a number. It's a complex number. It's still a constant, right? If I take the derivative of this thing, what's the derivative of e to the a constant times e to the at? Yeah. Just like that. So this guy becomes 0.1 times magnitude b times j 300 times e to the j angle b times e to the j 300t, like that, plus 3 times b e to the j angle b times e to the j 300t, like that. And that's all equal to this guy. Now, it's starting to look pretty ugly, but there's a nice thing that just happened here. What's true on both sides of this equation? Isn't there a term that's in everything? E to the j 300t is everywhere, and thus it disappears. Which is nice. All the time dependence is gone. There's no dependence on time anymore. That's the magical step that will ultimately allow you to stop doing differential equations in 2112, right? The fact that all time dependence just left means I don't need the d by dt's. I just need to know what they do, right? And I can skip some steps. Skip a lot of steps, actually. All right, so that basically that leaves me with an equation that is 0.1 times j 300. And let me just combine that a little bit. What's 0.1 times 300? Yeah, so it's got to be j 30. plus over here, I would have a 3. And if I look at this carefully, I also have a magnitude b times e to the j angle b in both terms as well. All right, I did a lot of algebra simplification to get from that step to that step. Right, what did I do? I basically saw that I have a magnitude b and e to the j angle b in both terms. And this guy I just brought down. Okay. So I did that on purpose because I don't want to spend a lot of time on it. You can figure out the algebra later. How many equations is that? How many equations is that? A trick question, right? It's one, isn't it? It's two. There's actually two there. I can turn it into two. Yeah, yes, it's one, right? But I can turn it into two, right? How can I turn it into two? Well, I've got something times a complex number equals something. So complex number times complex number equals another complex number. So I can make one equation for what and one equation for what. So complex number times complex number equals another complex number. So how can I turn that into two equations? Well, no, nothing negative or positive about this guy per se. I think you're thinking of the vectors rotating piece. That's the Euler's identity thing. This is more simple than that. One complex, so A times B equals C. What do I solve for when I do A times B equals C? If I'm trying to find C, okay, so if I told you A times B and they were complex numbers, how would I find that product? So like I said back at the very beginning, go back through my notes, you could FOIL if I have them in Cartesian form. That's usually not the way we approach it. If I have two complex numbers, multiply the magnitudes, add the angles, right? That's what I've got here. I have these two guys together, right? So these two complex numbers equals this complex number. So I know that the product of their magnitudes is equal to the magnitude of the product. And what do I know about the angles? The angles of the two sum to the angle of the other. Okay, so how do I turn that into? So I'm going to solve for the components of this. So what do I have? I had 30, what was it? 30J plus 3 times magnitude of B, e to the j, angle B equals 4 e to the j, 20 degrees. All right. I take the magnitude of both sides of this thing. This is something you better know how to do, right? If I take the magnitude of both sides of this thing, what's the magnitude of 4 e to the j, 20? 4, right? The magnitude of 4 e to the j, 20 is 4. What's the magnitude of the other side of the equation? So this side. So how do I get the magnitude of 30j plus 3? Square root of 30 squared plus 3 squared. Okay. And then what about the b e to the j angle b? What's that guy? Just magnitude b, right? I've got one equation that came out of that, right? Magnitude of b equals 4 over 30 squared plus 3 squared. Whatever that is. Okay. There's also an equation for the angle. Okay. What's the angle of the right side? 4 e to the j, 20. What's the angle of that? 20 degrees. Right? 20 degrees. What's the angle of the left side? So it's the angle of this plus the angle of this. The angle of the b e to the j angle b is angle b. Right? What's the angle of 30j plus 3? Inverse tan of the imaginary part by the real part, like that. And so I can solve that to say the angle of B equals 20 degrees minus arctan of 10. All right. So I'm all set at this point. I actually know what this steady state result is, right? And the steady state result that I get is, if I plug in numbers here, if I plug in these numbers, this guy becomes 0.3127. 0.3127 if I plug in numbers. This guy becomes negative 64.2894 degrees. Okay, so by the time I'm all done with this thing, all right, I am left with B e to the j angle B right. This is what we ended up, we put this into the equation, right? And what we ultimately said was, okay, so this is equal to, apparently, I'm going to leave it that way for a second, right? All right, we're going to go back to these numbers here. We're going to leave it this way for a second, right? What we did originally, if we go all the way back to what we did, is we converted the whole equation into complex exponential. And instead of guessing that we had a cosine, we used this approach right here. And we said that cosine is the real part of that whole thing. So if I do this, I got to get back to the real part of this guy. All right, that's the final thing I need to figure out how to do. So if I looked at this right now and I said, all right, using Euler's identity, expand that for me with Euler's identity, because you should be good at doing that by now. What would I do here? I'd say it's magnitude B times e to the j what? What would I have up there in that j? E to the j what? Yep, 300t plus angle B. All right, how does that expand using Euler's identity? Yeah, so if I have e to the j theta, how do I expand? So Euler's identity says e to the j theta becomes what? Cosine plus j sine. So this guy becomes cosine of 300t plus angle B plus j times magnitude B sine 300t plus angle B, right? So if I said to you, what's the real part of that? What is the real part of that? The cosine term. Yep. So what I do is I take the real part of this whole thing. And I say, ultimately, my particular solution was B cosine 300t plus whatever the angle of B was. So based on what we just said, it's 0.01327 cosine 300t minus 64.2894 degrees, like that. So I've got three basic steps in my solution process, right? Get the transient, get the steady state, solve for the unknown coefficient. If I have a sinusoidal input, I basically just created 5 steps to step 2. All right, it was basically what I did. And I walked through that pretty slowly, but it's fairly straightforward once you get used to it. So what I end up with is this guy right here. And I wrote 0.1327, but it's actually 0.3127. All right. I'm gonna write that. All right. So this is the last step. The last step is to combine those two things, right? The transient and the steady state. Now, in the last step, I find the total solution. All right, what's unknown to me at this point when I'm looking at this? Well, what I don't know is that constant on the transient response, right? How do I solve for that? Using the initial condition. So the initial condition here was I was told that at time t equal to 0, y of 0 is equal to 10. So I have 10. What do I do with this whole thing? Set t equal to 0. So I think my final notes, I called it A here. I'm going to call it A. A e to the 0 plus 0.3127. What do I do with the cosine? Yeah, I plug in t equal to 0. So this whole thing, if I plug in t equal to 0, it becomes minus 64.2894 degrees. And I solved to find that A is equal to 10 minus 0.3127 cosine of negative 64.2894 degrees, like that. Okay, so here's the graphs. Okay. Now, what did I do here? You can look at my code carefully later. All right, if you want to see how I approached this, right, and follow my approach. But what I did, just like I did in the homework, I basically asked you for 3 different graphs: the transient response, the steady state, and the total solution. Help me out. Which one is which? All right, let's start with well, I don't know, you tell me which one you want to start with. How about the red? Start with the red, this guy. What is that? Look, all pictures of the code. That's good. Yes, the steady state. How do you know it's the steady state? Yeah, it's just a cosine always. All right. This is the steady state. I call that YP. What about the other ones there? What are they? There's actually 2 there. It might not look like 2. There's a blue and a yellow. The transient is just the exponential, right? So the blue here, the blue is y sub c. The yellowy here is y equal to y sub c plus y sub p. So it looks like the sum of the 2, right? Like it should, right? It's basically what you see is this added on top of that line that's shifting around. And what do I notice? I should always notice that by the time I get to steady state, what's true about the steady state and the total solution? And the total solution is the yellow. The red is the steady state. What do I notice by the time I get to here? They pretty much aligned with each other. Why is that? Because what's a transient supposed to do? By its very nature, a transient does what? If something is transient, the meaning of the word transient is that it's here for a little while and then it's gone, right? That guy is gone and eventually over with. So 2112, you're going to spend time at the beginning, you're going to be talking about transient responses, but then you basically stop. Because most of the time the world's in steady state, right? When do I have transients? Well, when I push the power button, right? There's a transient of some kind, right? But shortly after I push the power button, everything should be in steady state. The system's running, okay? So how long did it take for that to happen? That's something we have to talk about more next week. How long did it take for me to get to steady state? Technically forever. It takes to infinity, right? But approximately we say it takes how long? So if you've gone through 2111, you should know that it's 5 tau, 5 time constants. Okay. I'm going to talk about in some more detail for the project. All right. But basically it takes a couple of time constants, usually by about 5 time constants, where I haven't really described what that is. Right. It steadies out. All right. This is, you got the last problem on the homework is basically just like this. Solving the transient Super easy. All right. You should be able to solve the transient pretty much in your sleep, right? Because you're basically just getting some equation that's like S plus something equals 0. And you're solving for S, right? That's basically all it is. This part's a little bit harder, right? What we just did here with the sinusoidal input. But you guys should be, this is part of the reason why I have this on the homework before exam 1. This is good practice for exam 1 because it's really just the stuff that's on exam 1, right? You're using it now for a real application. Okay. All right. We're gonna do more of these examples. We're gonna plow through examples basically on this stuff over the next couple of days, but I got to get into second order. So you don't have any second order on the homework due tomorrow, but you will for the homework due next week. Okay. So if I have a second order differential equation, what makes this thing second order? Second derivative. All right, that's a math way of saying it. From a physical perspective, why do I have two derivatives? Not two inputs. Two energy storage elements. All right, two storage elements. So if I'm talking circuits, I'm talking what? I'm talking L and C. All right. And they can interact with each other in funny ways that cause those oscillations like we were seeing. Right? In fact, I can make it such that it only oscillates. I can actually make these so that the transient never dies. All right. And that is a possibility, and you can do it. And that's actually common. Everybody in the room has one right now. Right? What one thing does everybody have right now where the transient response never dies? Any idea? Well, that's not that. Yeah, good answer. Not what I was going for. Any ideas? What kind of circuit do you have? Your phone. Your phone has a transmitter circuit, right? And it's transmitting at 2.4 gigahertz. This makes a sine wave somehow. That sine wave is the transient response of that circuit, and it never dies. It just goes along making a 2.4 gigahertz sine wave. That's a problem we're going to do later on. All right, figure out how that would work. All right, it's basically a circuit with an L and a C and just an L and a C. No resistance, right? That sounds hard to do. There's always resistance, right? But somehow I can overcome that resistance perfectly. All right, if I do it right. Okay. Anyway, that's not important for solving differential equations. Wait, what's that? I have to use magic to do it, but I can do it, right? In other words, what I have to do is I have to use an active approach, which means that I have to come up with a control system that basically always balances the resistance if it starts to change on it, right? So I can make a negative R using transistors. That's what we do ultimately. Okay. But anyway, that is not a topic for concern of any of you right now. Your concern is, hey, I gave you a differential equation, right? It's second order. I need to solve it, right? So my general form for this guy is that it looks like this, all right? Now, I have a lot of formulas in here that you're going to want to go back to later. The thing for you to remember is that all of those formulas assume that the differential equation has this form, all right? Which means that there is a 1 right here. So if I give you something where there's not a 1, what would I have to do? Divide both sides by whatever that coefficient is, and it turns into this form, all right? Because I may give you 1, and you start using my formulas, and this has a 3 out there, and it won't work. All right, you have to do an extra step to do that. All right, B and C are both constants, okay? So our solution has this form. Same as it did for first order. YP and YC. All right, just taking a break for a second. YP and YC, what are those? What did I call? What is YP? What's the name I give for that? Particular or my term, which is a little bit more, I don't know, engineering-y is steady state. And Y sub C is the characteristic or homogeneous or transient. All right. All right, so how do I solve for it? Wow, it's the same 3 steps, right? Solve the homogeneous equation. That gives me the transient. Solve the non-homogeneous equation. That gives me the steady state. Put them both together and finish. Question with these guys. Talked about at the beginning. When I get the transient, what's the transient going to have in it? What's going to be in the transient for the second order? Two exponentials, right? Two exponentials. And so I'm going to have two unknown coefficients, which means how many initial conditions do I need always? Two. Okay. So we'll always need two initial conditions. So that means I have one initial condition for the output y. And I also have to have an initial, so I'll need y of 0. And I'll also need one for what? Yeah, the derivative, dy by dt of 0. Okay. Or y prime of 0. All right, so I'm going to need two. All right. Here's our general form of this thing. All right. So I want to solve the homogeneous equation. Is this the homogeneous equation here? What is the homogeneous equation that goes with this? Let x, so yeah, let x of t equal to 0. So I also say that the solution to it is y sub c. So I get this guy plus b times dyc by dt plus c times y sub c of t equals 0. This is the corresponding homogeneous equation. Okay. All right. So what do I guess for y sub c? I always guess. What do I guess? I'm going to guess that it's y sub c of t is equal to c e to the st. With what caveat? C is not equal to 0. All right? So if I plug that in here, I get, let's see, d squared by dt squared of c e to the st plus b times d by dt of c e to the st plus little c times c e to the st equal to 0. So help me out with the derivatives. So if I have the derivative of e to the st, what's the derivative of e to the st? S e to the st. What's the second derivative of an exponential? I'd bring the s down twice, right? So this whole thing would become c s squared e to the st plus b times capital C s e to the st plus little c capital C e to the st equals 0. Help me out with that. I can factor that into three things multiplying each other as well, can I? What would they be? C e to the st times what? S squared plus bs plus little c equals 0. Three things multiply each other. What has to be true about at least one of those three? At least one of them has to be 0. And which one is it going to be? The s squared. Yeah, this guy we call him the characteristic equation because he tells us a lot about the characteristics of this thing. All right. So I have s squared plus bs plus c equals 0. What did I miss up? Okay. All right. Before I go to my next slide there, I'm going to go up here. S squared plus bs plus little c equals 0. All right. Somebody's time to shine. How do I solve that? What do I call the solution? What do I call this? What kind of equation is it? The characteristic equation. If I gave it to you in high school, you would have said this is a quadratic, right? So how do I solve a quadratic? How do I solve for the roots of a quadratic?
Quadratic formula, factoring, or continuous square.
Yeah. So well, okay. Yeah, all of those things. So you can always do factoring. Completing the square, I guess you could always do too using complex numbers. Right? It's not easy to do. Quadratic formula is the easiest approach. All right, quadratic formula. Where does this start? Somebody other than the guy in the red shirt. Negative b plus or minus the square root of what? b squared minus 4ac
Yes.
all over 2. An a in this, I don't have an a in this guy, right? So it's just that. Now, important thing, real part will always be negative. Real part, what am I talking about? How did I jump to real parts already? What's important about this whole thing? What's important about that solution? Well, the result here, so basically what do we just find? Basically we found is there's always going to be 2 exponentials. Why? Why do I know there's always 2 exponentials? How many solutions, how many numbers do I get from this guy? I get 2. I get, so 1 for the positive root, 1 for the negative, right? So I get 2 solutions. I have 2 exponentials, right? Got the 2 exponentials out. However, what's really important on this whole thing?
Always negative.
What's always negative?
That.
Kind of, sort of. This guy's complicated, right? What's important in this result here? What's important? All of it's important, right? But what really determines what this guy looks like?
Oh.
What's under the square root? So b squared minus 4ac really controls this. If that's positive, both of my roots to this thing are real. If that guy's negative, then my roots are complex. And if that guy is 0, I get 2 roots that are exactly the same. Now, in no real world sense do we ever have 2 roots that are ever exactly the same. But basically, we come up with 3 different forms to that solution. All right? 3 different forms to the solution. So basically, what are the 3 different forms? All right, so basically they are this. So what I did was so each of these guys, you'll see, I said that my solution to this is negative b plus minus b squared minus 4ac all over 2. Okay. So I got 3 different cases that I consider here. And I usually start with this one here, what I call the undamped scenario. In the undamped scenario, what do I have? I basically say, in that particular case, b is equal to 0. And I get that the 2 roots are purely imaginary. So always, the transient response is this. C1, an unknown constant, times e to the s1t, plus C2, an unknown constant, times e to the s2t, where s1 and s2 are the 2 roots of that thing. Okay. Each of these cases, there are 4 different scenarios that I wrote out there. The 4 scenarios are this one here, where it's underdamped. This one here would be where b squared minus 4ac is less than 0. This one is where b squared minus 4ac is equal to 0. And this one here is where b squared minus 4ac is greater than 0. The top one is if b is equal to 0. Okay, which is a special case that happens sometimes. In all of those cases, with the exception of what I call the stupid case, the critically damped case. It's stupid because it never happens in the real world. All right. With the exception of that one, all of the roots or all of the solutions, like this one, all look exactly the same. Okay. What I do is if I plug in that S is equal to the form of the solution that I have in each of these cases, right? If I plug those in, like just think about this one here, where S1 is J square root C. This one is negative J square root C. If I put those together, we know kind of already now from our Euler's identity stuff that that's going to be a cosine. All right. Somehow, if you plug these into here, you would find this. Okay. Similarly here with this one, I would see that I got also a cosine. What's the difference between this one and this one? Second one is multiplied by an exponential, which will always be real. right? If I look at this, what I see is real part plus j imaginary part. Real part minus j imaginary part. Okay. What do I call these two guys? S1 and S2. Conjugates, right? So the difference between these two here, this one has a transient response that never dies. This is the really special case that it can happen. All right. This one here, what's going to be true about this? If I wait long enough, yeah, it's got a cosine in it, but if I wait long enough, what's going to happen to that cosine? It'll what? It will approach zero. Why do I know that it'll approach zero? What do I know about e to the something t? It approaches zero as long as something is negative, right? So really, what should always be the case in these things is the real parts of the solution will always be negative. All right. In second order differential equations, the real parts always better be negative. All right. That will always be the case, right? The problems you have in 2112, the real part will always be negative. What would happen if the real part was positive? It tells you that the transient response basically becomes infinite, right? Which nothing in the world ever becomes infinite, right? At some point, capacitors explode, inductors catch on fire, something happens, right? If you really got in that situation, there would be an explosive event. Nature's just not set up to do that. Okay? So I can relate all of these sorts of things. The terms that I have right here, when I omega d, I can relate that to b squared minus 4ac. Right? I've got summaries of all that stuff here. Right? Basically, this is the critical step. So on Tuesday and Thursday next week, we're going to spend a lot of time talking through sort of examples of different types of these responses. We're going to go through a couple of examples of each one, but you can imagine what your homework's going to be next week, right? You're going to be solving basically a bunch of these sorts of things. Step 2, the steady state part, exact same as it was for first order, exact same. I follow the same solution approach if I've got a sine wave. Now, the third step, basically where I find those unknowns in the transient response, right? What I end up with is I have two initial conditions, right? So I basically have to figure out the derivative of the solution and the solution. And then I basically go through a solution process. Now, what I've done here, there's a lot of stuff here. We can walk through it slowly later, right? But basically, I gave you a pretty clear process for figuring out how to solve for those unknowns when you get to that step. All right. We'll do the examples of that in some detail next week. But let's say I had this guy, right here. So I got sinusoidal input again. Okay. I want to do the first step because the first step is fairly easy to do. And we can do that in the 4 minutes that we have. So how do I do the first step? How do I find the transient solution here? Set it equal to 0. So basically I say d squared y p by dt squared plus 4 dyp by dt plus 3yp. Sorry, I don't use p for these. I use c. Okay. And then I always guess that it has to be y sub c equal to a constant times e to the st. But if I plug all that stuff in there, what is supposed to happen? What do I end up with if I plug that thing in there? I get my characteristic equation. How can I jump from this straight to my characteristic equation? There's no need for me to do the derivatives and everything every time. How do I jump to that? Turn s squared plus 4s plus 3 equals 0. All right. Now, this guy, I could use the quadratic formula, all right, but I can actually see that this guy works out to be s plus 3 times s plus 1. All right. And so s equals -3 and -1. Right? So my y sub c ends up being C1 e to the negative 3t plus C2 e to the negative t. All right, which of these is that one? Which of these four choices did I just get? If I had just exponentials here that were purely real, I can't start making cosines and stuff out of that, right? Which one did I get? The overdamps, basically where they're both real, right? They're both real. And I ended up with that, right? So it's fairly straightforward to figure out those. The hard part becomes then when you start combining everything together, right? But really, there's a pretty straightforward process for these. They're not that hard to do. It looks a little bit overwhelming, but once you start getting into the process, you see that it's fairly straightforward. Now, in MATLAB, what I will typically do is I will solve this thing. MATLAB basically has an approach where it looks at an equation like that, or what I do is you look at this and you basically tell it what the coefficients are. There's a function called roots, which will tell me the roots of a polynomial. So if I have a polynomial s squared plus 4s plus 3, I give it a vector that has the polynomial, the coefficients in the polynomial. So I'll say the squared term, the middle term, the zero order term, like that. So what I just did was I just put the second order, the first order, and the zero order term coefficients together. This roots function will tell me what the roots are. All right. And I use that a lot. You'll see that in my example code. I always use that. All right. Not to say that I couldn't factor that. All right, but I like using MATLAB to do it for me. Okay. All right. I'm gonna stop there. We'll do the rest of this one on Tuesday.